To thank the organizers for the invitation to present our work here. And today I want to tell you a bit about some of the work that we have been doing in my group at the University of Oklahoma in terms of enhancing quantum properties of light in order to enhance them. This work was done in collaboration with Oak National Lab and it's been funded by the Keck Foundation. And one of the long-term goals or things that people have been trying in quantum optics is to use quantum phase of light to enhance the light. For us, we're particularly interested in using the reduced noise properties of quantum phase of light in order to enhance sensors. And the question that we ask ourselves, is it possible to do this with real light devices? And we think the answer is yes to the use of plasmonic sensors. And the reason why we chose these devices is that they're actually already used in commercial devices, and they're widely used for chemical and biological sensing. One of the nice things about these sensors is that they can be probed with light, so that means we can actually interface with quantum phase of light. And they have also been shown to operate at the short noise limit, which means that in principle, we can then use the reduced noise properties to go below the current operation and enhance them further. As I will show later, these sensors are actually used to detect small changes in the index of refraction locally. So the goal of this project was to show that we can enhance the sensitivity of these sensors for the detection of smaller changes in the index of refraction. In order to be able to achieve this goal, we need three different ingredients. We need a source of quantum phase of light, we need the plasmonic structures that will act as the sensors, and we need a way to calculate the entanglement properties of the light after interacting with the sensors. So I will start my talk by briefly describing each of these ingredients. I will first describe the source. We use four-way mixing to generate entangled beams, some of the entanglement properties. I will then explain how we actually calculate entanglement properties in the system. Then I will give a brief overview on the properties of the structures that we use as sensors and how they can operate as sensors. Once we have all these parts, I will put them together to describe two experiments that we have done. The first one is in terms of transduction of entanglement through the structures, and the second one is in terms of using these structures as sensors. Okay, so let's start with the source and how we can characterize it. So, in order to generate twin beams, we need a nonlinear process that can emit two photons into the field, and typically optical parametric oscillators are used, where you have a nonlinear crystal that's based on parametric sound conversion, and you put this inside a cavity, and that allows you to enhance the nonlinearity and obtain large levels of squeezing or twin beams. We use four-way mixing in our system, in an atomic system, and what we have in this process is that we absorb two pump photons, emit a probe and conjugate photons to come back to the same energy level. And the main thing to find right here is that these photons are always emitted together, they're always emitted in pairs, and this is what leads to a quantum correlation system. So as you can imagine, the fact that every time we have a photon here, we have a photon here, it means that we're going to have amplitude correlations between the two fields. So if we look at a phase space diagram of the probe versus conjugate amplitude, we're going to get an ellipse at 45 degrees. And the quantum nature of this correlation is given by the fact that the correlation uncertainty is going to be smaller than the standard quantum or the short noise limit at a given direction, the amplitude difference. We also have, in addition to emission of photons in pairs, we have conservation of energy. This also leads to phase anti-correlations in the process, such that now we have, if we look at a phase space diagram of the phase quadratures, we have something at minus 45, and we're going to have squeezing along the phase. As we will see later, measurement of these two joint quadratures will be enough to characterize the entanglement properties of our beam. So how do we do this in the lab? We actually use a non-linear four-way mixing in a double lambda system in the D1 line of Rubicon 95. What we do is that we take a strong pump beam, and this pump beam is going to act as the two pumps that are needed for the four-way mixing process. We combine that with a probe beam inside a cell, and as a result of the four-way mixing process, what we get is amplification of the probe beam and generation of the new beam, the conjugate itself. The energy level structure is slightly different than the one I explained before, but the idea is the same. We absorb a pump, emit a probe, absorb a second pump, emit a conjugate. Every time we have the four-way mixing process, we generate probe and conjugate in pairs. So the first thing we can do is characterize the quantum properties of the system by making intensity noise measurements. So what we do is that we look at the intensity of the probe, intensity of the conjugate, and look at the noise in the difference. When we do this, we get measurements like this. So what we have here is the noise spectrum. The green line corresponds to the noise that we get when we do the measurements of the intensity difference of the probe and the conjugate. That is the twin beam intensity difference for the four-way mixing. We can calibrate the short noise limit by taking coherence states of the same power, and we get the blue line here. And what we can see here is that we're able to get 9 dBs of squeezing or noise reduction with this process. And this corresponds to having only 13% of the short noise limit left in the relative intensity between these groups. These measurements, while they tell us that our beams are quantum, they're not enough to tell us about the entanglement in the system. To learn about entanglement, we have to do something slightly more complicated, and we're going to be using the interpolate criterion that was developed in these papers that tells us that the sum of the noise in the amplitude difference and the phase sum has to be less than 2, where we have normalized the short noise limit for each noise quadrature to be equal to 1. So what does this mean? This means that if we have squeezing in both the amplitude difference and the phase sum at the same time, then we know that we have continuous variable entanglement. In order to perform these measurements, we have to do homodyne detection to be able to access both quadratures of the fields. And we have one homodyne detector for the float, one for the conjugate, and we do things in a way that we synchronize the scan of the local oscillators, such that when we measure the amplitude quadrature here, we measure the amplitude quadrature here. When we measure the phase quadrature here, we measure the phase quadrature. This way, when we look at the sum and the difference signal, we can directly measure the joint quadratures that we're interested in. So what we get typically, if you've seen any squeezing papers, you see something like this, at this kind of phase of the local oscillator. You get something that goes between the minimum noise and the maximum noise of your allele distribution. And what we have here is that the red signal corresponds, the minimum of that corresponds to the noise in the phase sum. The minimum of the blue one corresponds to the noise in the amplitude difference. And as we can see here, we have about 4.3 degrees of squeezing. When we change this interpolated parameter in linear scale, we get about 0.74, which tells us that we have entanglement between the quadratures of these two fields. Wrong computer. So the other thing that we need to have in this process is that we need to have phase matching. That is, the process needs to conserve momentum, which means that the k vectors for the two plumb photons that are absorbed have to be equal to the k vectors for the probe and the conjugate photon. So what this means is that the directions of the probe and the conjugate are going to be determined by this phase matching. And it means that the direction of the beams is anticorrelated, especially the probe beam is emitting in one direction, the conjugate is emitting in the other, and they're always completely anticorrelated. And we need this phase matching in order to have an efficient Fourier mixing process, but this is not a non-enough thing. It turns out that there's a range of angles which we can have between the beams in order to generate the distant angle beams. And what this leads to, if we look at the source and the emission region in the far field, what we have is a region that is shaped like a donut over which we can emit these entangled photons. If we combine the fact that we have a large range of angles over which we can emit photons with the fact that we do not need a cavity around our system, we have then a system that can support a large number of spatial modes. And in order to illustrate this, what we can do is that we can create a mask at the input probe beam. In this case, it has a shape of the number 200, and look at what we get at the output. So what we get at the output is shown here, where this is the amplified probe, this is the generated conjugate, and as you can see, it has a shape that resembles the photon. Rotated by 180 degrees in order to conserve momentum just because of the phase match. So this doesn't really tell us anything about the quantum properties of this field. This is just a spatial distribution. The nice thing about homodyne detection is that we can actually use it to determine the entanglement that we have between such complicated spatial patterns or images. And you can do this because the local oscillator actually selects the shape of the mode that we're measuring with this detector. So if we have local oscillators with a different given spatial pattern, we're actually detecting the properties of that spatial pattern. In this particular case, for example, we use a local oscillator with the shape of a T, and we repeat the same type of measurements, and what we find is that we still have entanglement between these images or complicated spatial patterns. Okay, so the next ingredient that we need for our experiments are the plasmonic structures. I first want to tell you how we can use these plasmonic structures, and I'll explain what they are in a second, how we can use them as samples. So what we actually have is an array of nanoholes in a thin metal film, as shown here. So we have a thin metal film of about 100 nanometers in thickness, and then we have an array of holes. And the operation of these structures as sensors is based on two main principles. The first one is known as extraordinary optical transmission. What we have in these structures is that these holes are actually subwavelengths. If we were to think about diffraction theory, we expect no light to go through. However, what we have in these structures is that light is incident on the structure, photons get converted to plasmons. Plasmons on one side then transfer the information to the plasmons on the other side, and that then re-emits the light on the other side. And this allows you to transmit large amounts of light through these structures. And this is the reason why we can actually probe these sensors with light. The other nice thing about these structures is that there's a resonance as a function of wavelength. So if we look at a transition as a function of frequency, what we get is a resonance peak like this. So if we were to probe the system with a single laser frequency, what we would get is a given transmission. So what happens next is that if the substance of interest, that is if we're trying to take some substance, it will introduce a local change in the interrefraction around the sensor. This will lead to a shift in resonance, and that as a result would lead to a change in transmission. So what we're going to be doing is we're going to be taking changes in transmission, and that will allow us to infer the change in interrefraction that happens around the structure. So in order to see how we can actually enhance these sensors through the use of quantum states of light, we need to understand a bit better what limits their sensitivity, what leads to this minimum resolvable change in the refraction. And it's actually composed of two parts. The first one is how much of a shift, that is how much the transmission changes when we have a change in index, and this is actually a property of the sensor itself. If we go back to kind of the diagram that we have here, this is kind of related to the slope that we have here, such that if we have a steeper slope, we will see a larger change in transmission, and this will allow us to detect more changes in interrefraction. The second part is the one we're more interested in, that has to do with the properties of the light. It includes things like the noise and also the intensity of the light. And this is one of the main limiting factors. So what is the minimum change in transmission we can detect? It's actually given by the noise in the measurement. So we have two transmission levels where we can distinguish the noise, then we can actually resolve that. But if the change in transmission is too small, such that the noise, the signal, or that the change in transmission is buried in the noise, then we're not able to resolve that change in interrefraction. So the idea here is to have reduced noise states, that is states that have reduced noise, such that we can reduce the noise in the measurement, and as a result are able to detect smaller changes in the interrefraction. So again, this points to two mechanisms to enhance the sensitivity. First one is to use reduced noise to quantum states of light, which is the one that we're actually going to focus on. The second one is to change the slope of the transmission spectrum. And this can be done through the design of the plasmonic structures. So for our structures in particular, as I mentioned, we use an array of nanoholes. We use a silver as our metal. And the array itself is 200 by 200 microns. This is an SEM image. If we zoom in, what we see is that we're actually using triangular holes for our system. The holes are about 200 by 200 microns in dimension and 400 micron spacing between them. For our particular wavelength of 795, we're able to excite localized software plasmons, and I will explain later why we care about this. And as I explained before, this leads to EDOT. And for some of the experiments we're doing, we're actually going to be using two structures. So this is just the measured transmission spectrum as a function of wavelength. And what we see is the resonance that we expect. And at operational wavelength, we're able to get for one of the structures 65% transmission, and for the other 50% transmission. Again, this is significantly larger than what we would expect just in diffraction theory if we were to calculate that for the structure. Okay, so now that we have all the ingredients, I'm going to talk about some of the experiments that we performed. As I mentioned, the goal of this project was to enhance the sensitivity of plasmonic sensors. So the first thing that we checked is whether this transduction, that is the transfer of photons to plasmons back to photons, actually conserves the quantum property. If it doesn't conserve the quantum property, then there's no hope of using these structures to enhance the sensitivity when there is a sensor. So the first thing that we did was just to show that the plasmonic structures can maintain the quantum properties of entangled images. So what we do in order to do this experiment is shown here, where we take our source of Powell mixing to generate entangled probe and conjugate beams. We take these two beams and send them to two separate and independent plasmonic structures, and then we characterize the properties by doing homogram detection. In order to do this, I'm not going to go into details of why we do this, but we actually use a second four-way mixing process in order to generate the local oscillators that are needed. And I'm just going to briefly mention that this allows us to actually study complicated spatial patterns because everything's really well mode matched, because it's generated with the same process. And just to reemphasize, what we have in this transduction or EOT process is that we're actually transferring, if we're able to preserve the quantum properties, we're transferring the quantum properties from photons to plasmons and then back to photons. So The reason why we're interested in these localized surface plasmons is that it has been shown that they're able to support a large number of K vectors. So what this means is that if we illuminate these with complicated spatial patterns that have a lot of K vectors in their angular spectrum, they should be able to transduce those without a significant loss in properties. It makes it easier to align the sensors and also to get more light through. So what we did, the first experiment we did is we take our source of wave mixing, use probe with the logo of the University of Oklahoma, and then use that to generate probe and conjugate beams. The first thing to point out here is that we have a slight loss of resolution from the input probe to generate probe and conjugate, and this has to do with the limited bandwidth of the four-way mixing process. Remember, there's a phase machine condition, so that limits the bandwidth, spatial bandwidth of the process. We then take these two images and send them to our two separate plasmonic structures, and the first thing that we can notice here is that there's not a significant degradation of the resolution, mainly loss in intensity. These are still classical measurements. We haven't measured anything quantum here, but this allows us to show that indeed these localized surface plasmons can support a large number of spatial bands. The next thing we can do is actually measure that what happens to the quantum properties of these images. And in order to do this, we perform that double balance homodynamic detection that I explained. But now we have the local oscillators with the shape of the University of Oklahoma logo. And we first characterize our source. And to do this, we remove the plasmonic structures through the homodynamic detection. And what we find is that we have about 3 degrees of squeezing in both of the giant quadratures that tells that we have continuous spiral entanglement. We then take the plasmonic structures, introduce them into the probe and conjugate beams, and repeat the measurements. What we find is that we still have about 1 dB of squeezing left that tells us, can anyone see this laser pointer or not? It's really weak. I don't know. Which one is it? All right, so that's better. So what we find here, the main thing is that the loss of entanglement we get is actually consistent with the losses that are introduced by the sensors. You remember, I mentioned that these plasmonic structures have 65% transmission and 50% transmission. So what this means is that this transduction process doesn't really introduce a lot of excess noise into the process. We're mainly limited by the losses introduced by the imperfect field. So now that we know that the plasmonic structures can preserve the quantum property, the next thing that we did was to actually use one of these structures as a sensor. And in order to do this, we have the following setup, where we again have our four-way mixing process. We generate probe and conjugate. The probe beam is sent to probe the plasmonic structure, while the conjugate is used as a reference beam. And then we do balance detection, where we allow the gain of one of the detectors to be optimized. And in order to perform this measurement, we actually have to place the sensor itself inside a well-controlled environment so that we can calibrate the actual change in refraction. In order to do this, what we did is that we developed a sealed chamber. We actually use an ultrasonic buzzer to introduce pressure waves inside the chamber, and by changing these pressure waves, we can control the change in index of refraction around the sensor. So we calibrate what is the change in index by placing the chamber in an interferometer. This allows us to calibrate what is the change in index for a given driving voltage for the piezoelectric. So in order to illustrate how this operates, what we can do is that we can drive the buzzer inside the chamber at its resonance frequency, which is 199 kilohertz. And what we get is a modulation in the transmission at this frequency, and as a result, we get a signal in the spectrum of the light. We first use the balanced coherent state configuration that has the same power as the probe and the conjugate, so we replace the probe and the conjugate by coherent states of the same power. And when we do a modulation of 1 part in 10 to the 7th of the refractive index, we get something like this for the coherent state, where this is the signal due to the modulation. When we repeat this measurement with the twin beams, we're able to reduce the noise. And what this means is the signal stays the same, we reduce the noise, so we're enhancing the signal-to-noise ratio, and as a result, should be able to enhance the sensitivity. Something to point out here is that the noise reduction we have with the twin beams is only 4 dB as opposed to the 9 dB we started with, and the reason for this is due to the losses that we have due to the plasmonic structure of the optics that we need to have around the system. In order to really illustrate the advantage of using the twin beams, we can reduce the change in the infrarefraction so about 8 parts in 10 to the 9. At that level, we're not able to really see a signal for the coherent state, but when we use a twin beam, the signal is still really well resolved. So in order to really characterize this properly, what we're going to be doing, or what we did, is that we will make measurements at the driving frequency of the buffer, and then we slowly ramp down the change in the infrarefraction and see at what point we're not able to distinguish the signal from the noise anymore. When we do this, what we get is shown here, where we have a signal. We're measuring the signal for a given change in the index of refraction. As we decrease the index of refraction modulation, the signal goes down until it reaches the noise. We're not able to distinguish it from the noise, which is given by these horizontal lines here. For coherent state, this is before the short noise limit. When we now do the same measurements with the twin beams, what we get is shown here. We get the same behavior, but the main thing to notice is that the signal, we're able to resolve the signal from the noise all the way down to lower changes in the index of refraction. So to actually get a characterization of the sensitivity that we have, we take this data, calculate the signal to noise ratio. For coherent states, we get something like this. And then we find the point at which the signal, we can resolve the signal from the noise with 99% confidence level. And we take this to be our sensitivity. For coherent states, we get 8.6 and 10 to the minus 9. When we repeat this measurement with the twin beams, we get 5.5 and 10 to the 9. So this is about 5 parts in 10 to the 9 changes in the index of refraction. So if we take the ratio of these two quantities, what we find is that we get an enhancement factor due to the quantum properties of 1.6. The question is this what we expect? So if you go through the calculations, what you find is the enhancement factor goes as 1 over the square root of the level of squeezing, and the level that we see the enhancement factor is actually consistent with the 4 degrees of squeezing that is left after probing the plasmonic structures. Something else that we have to worry about is what are the resources that we're using in order to probe these sensors. So if we consider the number of photons probing the sensors as a resource, a better classical strategy would be to use a single coherent state, not the 2 coherent states that we used for our previous measurements. In practice, it's really complicated to do this, especially at modulation frequency that we have because of all the technical noise. So what we do is that we actually perform measurements where we have 2 coherent states of the same power as the one that is probing the sensor, and use that to get a sensitivity, which is shown here. Then we take into account the fact that this configuration has twice the noise as a single coherent state, and from there we can estimate the single beam detection or sensitivity for a single beam state, which is on the dash line here. And even when we compare to this optimal classical strategy, what we find is an enhancement factor of 1.24. So the last thing that we were actually studying or trying to figure out is whether the measurement that we're making is actually the optimal measurement for these type of states. So if you remember, the way I explained the plasmonic sensor, what we're effectively doing is that we're measuring a change in transmission. So we can actually use the techniques based on the quantum temporal bound in order to determine what is the sensitivity for a given quantum sensor. And what this bound tells you is what is the best you can do independent of the measurement. So if you're able to saturate this bound, then that means you have the optimal measurement. So what we're showing here is the sensitivity in transmission measurement multiplied by the number of photons that are used to probe your system. For a coherent state, we get something like this. So something that we're able to do in conjunction with this and some other theories is that we're able to show that the Fock state is actually the optimum quantum state that you can use to probe transmission measurements, and that makes sense because you have a determined number of photons. If you lose an X amount of photons, you know exactly how many we lost, and we're able to count them. The problem with Fock states is that it's hard to generate Fock states with more than a few photons. So the sensitivity scales as 1 over the number of photons, so we want a state that actually has a large number of photons. For the twin beams that we generate, we can actually generate photon at states that have milliwatts of power. So we went ahead and did a calculation for the twin beams, and what we find is that if you have twin beams of about with 5.8 degrees of squeezing, you get behavior like this. As you increase the squeezing to 10 dB, which is more or less where we are, you get something like this. If you're able to increase it further to 14 dB, what we see is that it can actually start to approach the ultimate limit of sensitivity. So these states are significantly easier to generate than the Fock state, and they also allow us to generate states with a lot of power. The other thing that we are able to get from this theory is that our detection scheme actually saturates the bound. So this means that we're actually performing the optimum measurement that we can do for this type of systems, And we're now doing experiments where we're trying to really show the measurements coincide with the theory that we have here. So before I conclude, I just want to acknowledge my research group at the University of Oklahoma. They have been, they made all of these experiments possible. And in particular, I want to thank the people that have been involved. Jabbat, a grad student, Ashraf, postdoc, he's here in the audience. And Tim has been working mainly on the general bound theory part of things. There was a former student at the beginning of the project, Matt, and our collaborators at Oak Ridge, Rachel and Ben, that are helping us with the fabrication and design of some of these plasmonic structures. So with that, I would like to conclude. I have showed you that we can use four-way mixing to generate highly entangled beams of light and also have interesting spatial properties. I showed you that the transduction through the plasmonic structure specializes both the entanglement and the spatial property of the light, and that we're able to implement a quantum enhanced harmonic sense. If you want to learn more details about this work, I encourage you to go take a look at these two references that describe both experiments that I described today. Thank you for your attention.
Questions?
So at first I didn't notice the use of cavities, but your squeezing spectrum has a bandwidth.
Right.
The 90, but you don't have a cavity, so what is the constant bandwidth?
The bandwidth is set by the atomic system itself. So this is not optimized for bandwidth, we're optimizing for squeezing, so depending on parameters you get different things, but the bandwidth is the order of the natural language of the atom. So we get bandwidth of the order of 15, 20 megahertz. And the reason for that is that in the four-way mixing process, we need to have well, in the four-way mixing process, we need to have the D&O and the two-photon resonance. So that the tuning from the two-photon resonance is what limits the bandwidth. So we actually use the triangular. That's more because our collaborator Outreach had identified that structure could be made resonant with high transmission at our operation wavelength. So we're now designing different structures and looking at different possibilities of structures. It's polarization sensitive, so we just use one polarization that gives us the optimum transmission, yes. So yeah, we consider different structures to actually enhance that slope and be able to get more sensitivity.
Actually, I'll ask a question later to that. So will these different structures reduce the losses? Is that what you...
Well, we're hoping two things. One is that we can reduce the losses. Two is that we can increase that slope. So that way we will be two ways. We get more sensitivity from the slope, and by reducing the losses, we can take further advantage in the quantum properties of the light.
Are there any other questions? If not, then please try to